idea here is, there we go, okay. The idea is we want to do something with a quantum computer, for example, simulate nuclear physics. But these quantum computers that we have and will have are inherently noisy. So what does that mean to be noisy? Let's try an activity. So please follow along. If you have your laptops, which you all should, we're going to go to quantumcomputing.ibm.com. So everyone, please pull out your laptops if you'd like, or you can watch, but it's fun to do. So we're going to run on a real device. And we're going to run a simple circuit that you see here, this Bell state circuit. And we're just going to prepare it and make measurements and see what happens. So an example of a device that we could run on is given at the right here, and we'll see this on the website when we get there. And it has these error rates, which you can see here. Maybe it's a little small, but we'll see that on the website. So, okay, so I'm going to do this live as well, so please follow along. So here I am at quantumcomputing.ibm.com, and you might have to make an account. If so, it should only take a second. But the simplest way to do this is we can just launch the composer. The lab, which some of you might have been using, is for Jupyter notebooks. We could also do that, but let's just, in the interest of having a talk, have it be visual and use a graphical interface. So here's a circuit, and I've already done this, so I'm cheating a little bit. But you see on the left here, we have this table of operations, and these gates operations should all look familiar by this point. And you should see in the middle here, you have something that looks like a circuit diagram. So you can take these and you can drag and drop these into the circuit. And in our case, we want to do a Bell state circuit. So to do a Bell state circuit, we've seen that before on the first day. We can do a Hadamard and a C-naught. If we do a Hadamard and a C-naught, then the state that we should get is shown over here in the bottom left. We should sample 0, 0 with probability a half. Why that's not exactly a half is probably due to the noise on the device, or the noise model that the simulator is using. And we should also sample 1, 1 with probability 1/2. So that's the setup. And once you have this, we can try to run it. So let's do that now. Here's the fun part. You should try to, at least if you haven't done it already, run something on a quantum device. And so here I just have the public account. So this is what you would have if any of you signed up. And here's a list of devices that we can run on. So you get brief information about these devices, number of qubits. QV stands for quantum volume. If anyone wants to know what that is, you can ask, but I won't go over it now. And so let's pick one. The other important thing is the total pending jobs. So these are all public, and you want to pick one which is, well, to run quickly, not have a lot of jobs. So these are about the same. I used Nairobi last night when I did this. So let's click this here, and let's try to run a job. When we run it, we should get a little notification in the top left that the job was sent. And now it's a matter of waiting to see what we get. In the interest of the lecture, let's not wait. Let's see what happened last night. But that's the idea. Like I said, if you haven't run on a real device, it's fun to do. So I would encourage you to do that. So I did this last night, and here's what I got. So you can see that 0, 0, and 1, 1 are the most dominant bit strings. So that's good. But we also see 0, 1, and 1, 0. So does anyone have an idea why this is? Yes. Noise. Yeah, that'll be a sufficient answer for now. So noise can manifest in many ways. This can be due to measurement errors, it can be due to gate errors, and various things. And at the fundamental level, these are due to interactions with the environment, unintended interactions. So that's the idea. But you can see this device is pretty good. If you did this a few years ago, 4 or 5 years ago, it would look a lot worse, but it's looking more or less as expected. So that's pretty good. Okay, so if we're going to run on these devices, we have to do something to deal with this noise. The objectives that I want to get from these lectures are three things. I'm going to give you just a taste of error correction. Now, the thing about error correction is just to get a taste, it's probably going to take the full hour. We'll see how it goes. There's a quote that you either know all of error correction or you know none of it. So it's a pretty big topic, but I want to give you the key elements and principles to understand this. And then we're going to move into error mitigation. And I'll define the difference. The idea of error mitigation is we can't do experimentally error correction right now very well, but we want to be able to do something. And that's the idea of error mitigation. We'll do something with fewer resources. And then the third thing is in the lab, you're going to implement, or the hands-on section, you're going to implement one of these error mitigation techniques yourself. And this is called zero noise extrapolation. I picked this one because it's rather easy to implement and understand. And at that point, you have a pretty good grasp on what people do to actually run these things. And you'll be able to do that in your own experiments. So that's the idea. And like I said, I'm going to ask you to think, just so I'm not talking to you endlessly. So please do follow along. There will be various exercises outlined in red. Okay, so we know this. I'll go quickly. This is just a recap of maybe the first two days. We have qubits. These are complex vectors. And the general state is a linear combination. Good. Okay, we all know this. We have gates, and gates can be any unitaries, but I want to highlight the polys in particular. The polys are big in error correction. They're big in a lot of different places in quantum computing. So burn these into your memory. I'll define them later when we need them. But these are the 4 poly units. The last thing is measurements. I'm going to include this here. I think this was covered in the first lecture. But the idea of measurements is we have this set of operators that's normalized in the sense that you see here, and or complete, I should say. And the probability of an outcome is given by this overlap, psi, mi dagger, mi psi. And importantly, the thing to remember for error correction is the final state after obtaining an outcome will be the projection onto one of them that occurs with this probability pi. So that's going to be a very important fact for error correction. Any questions about the recap? This should all be with you. Okay, so history lesson. In 1994, Peter Shor came up with this, his famous algorithm. So here's the title. If you want to read the paper, if you haven't, I would encourage you to. There's a picture of Peter on the right. And people were very interested by this, obviously. People have tried to crack RSA for a long time, and no one could. And so Peter came up with this thing. They used a quantum computer. And naturally, it gained a lot of interest very quickly. However, there's skepticism from the community. So this paper, Maintaining Coherence in Quantum Computers, was exactly about this thing that we're talking about right now, noise. So Unruh was saying, there's no way you could ever do this. How could you control a quantum system so precisely and protect it from the environment so well? So in response, quantum computing is due to a lot of people, but it's hard to overestimate, Peter Shor's contribution. So in response, the next year, Peter Shor developed quantum error correction. So this is the sort of foundational paper for error correction, also by Peter Shor. And he called it a scheme for reducing decoherence. And in this paper, he introduced the 9-qubit Shor code, which we'll see in this lecture, actually. Not only that, but he had to have a three-peat. He, in the following year, came up with fault-tolerant quantum computing. So other people have done a lot of work on this again, but this is sort of the foundational paper. And I'll define carefully, in some sense, the distinction between error correction and fault tolerance in this talk. Basically, error correction is you make some assumptions that things are perfect. Fault tolerant is you get rid of that. Everything's noisy. So that's the idea. Okay, So we've been saying a lot, quantum computers are great. And they are the powerful devices. However, because there's more that you can do, there's more that can go wrong. So with bits, they can flip. That's sort of the error. They can also be erased. So 0 goes to 0, 1 goes to 0. But let's just say they flip for now. And that's a usual error model. With quantum computers, like I said, anything that you can consider a gate, you can also consider an error. So not only do we have bit flips, which we do, that's sort of the manifest with poly Z. We also have phase flips. And then, even more fun, we have bit and phase flips. So that's how you think about poly Y. So poly Y gets the short end of the stick a little bit in error correction. This is the only time you'll see it. And that's because it's the product of X and Z. And so you can really only think of two of these. And for whatever reason, people didn't like Y, so we stick with X and Z. So this is, in my opinion, the most important fact about error correction. So I just said that anything that could be considered a gate can be considered an error. So gates can be continuous. So errors can be continuous or analog. So how can we hope to correct these? Let's formalize this a little bit. Let's say we have some error E that introduces a relative phase. So we have the state alpha 0 plus beta 1. That was perfect. And some error happened where now in the phase of the one state is e to the I delta. So this could be infinitesimally small. There's one thing we can do for any error, including this one, which is we can expand this in the poly basis. Why can we do this? Well, it's a basis. So we can write this as sum of coefficients with the polys acting on psi. And so that's good because now it's sort of a discrete set. However, we didn't do too much because the E0s, what I'm calling the E0s, the coefficients, E1s, these could still be coefficients. So take a minute to think about and discuss with your neighbor maybe. Is it possible to deal with this? Can we correct these infinitesimal errors, these coefficients E sub I, or are we just going to sort of say we can't deal with this? We'll correct some things like the discrete set, and we'll just have to live with this. Take a minute to think about this, and shout out if you have any ideas.
Brian, but one question. I will even think that if they're infinitesimal, it's easier. You can, to first order, just ignore them. But you say as if being infinitesimal is the problem.
Maybe continuous is a better word than infinitesimal.
Okay, because you do not know the coefficient.
Yeah.
If it was a single that I apply randomly the x gate, you can just apply transform that.
Yeah, let's say continuous.
Okay.
Yeah. Could be any real number. Yeah.
I think the answer is yes, because we show that type of action with the idea doesn't rotation on the lines into the statement. Makes sense to me. So use that as the basis of X and Z as rotation. Turn it back to the original one.
Okay.
But then you will need to know the coefficients. But you could do this from the thing many times.
I understood that the coefficients are not changing. You just have the I delta. But that's the error. Alpha and beta stay the same, right?
Alpha and beta are given, they're the original state. And then we have this e to the I delta, which is transformed into the coefficients E0 through E3, which are static, that they're not changing, but they're there, it's something. Yeah.
I do understand, I think that like quantum error correction takes more of like a statistical approach, but I guess if I was seeing this problem in a vacuum, my first intuition would be to look at like classical error correction, like handing codes and variables and stuff like that.
That's a great connection and great idea. And with classical, remember, you don't have this continuous problem. With classical, it's 0 to 1 and 1 to 0. And that's it. There's no e to the I delta here. So phase is nice, but not with errors. Yeah, but great idea.
If you knew the coefficients, you just apply the inverse transform. You do not, I guess you do not know the coefficients, otherwise it will not be an error.
You don't know.
If somebody put them there and you just correct. But if you have your computer, you can send a state that you know, I should have recovered alpha 0 times plus beta 1. I'm not recovering that. What is the anti thing that I need to do to come back? You cannot measure the wave function, so you will not measure that. You can measure statistically some projections until you get most likely the coefficients are.
Okay, great ideas. This is really great. I'm glad you're thinking. I'm still asleep, so you guys are thinking. That's good. So, yeah, can we measure or can we not measure? We're going to see this is the key to solving this. So the answer will be yes. We can deal with this. We can deal with continuous errors. And okay, I hope I piqued your interest now. So let's see how it works. Measurement is the key, like I said. Measurement is a key step in error correction. It's going to map continuous errors to discrete errors. So what does that mean? So let's say we have this error state, like I said, and let's choose some set of measurement operators, which we'll do in error correction. And as I said at the start in the review, with probability pi, we're going to get one of these. So we're going to get one of these, mi acting on e, this projection. And now let's be nice to ourselves. And well, okay, so first, this is going to collapse the superposition, so to speak, and going to make the continuous coefficient a global phase. So that's the sort of key thing of how you can deal with the continuous coefficients. Global phases won't matter. And so to see this, we can say, for example, we can choose these mi, just be nice to ourselves, such that the error state, E psi, becomes some eta I sigma I acting on psi. So sigma I is now one of the polys, I, x, y, or z. And eta I is now this, this continuous coefficient, or related to it. And so because of this, we now have sigma acting on psi, but it's one of the sigmas. It's one of the sigmas. It's one of four things. If you got identity, nothing went wrong. If you got poly x, then you had a bit flip, etc. So that's four things. That's a discrete set that you can now correct. And now the key thing about the eta I, the continuous coefficient, is it's a global phase. Global phase do not influence the measurement statistics. And so we don't care about that. It could be infinitesimal, it could be continuous, it could be whatever. It's there, but it doesn't matter. Questions about this? There's a nice quote. This is not stressed a lot in many textbooks. There's one which it is, Eleanor Riefeld's textbook. Eleanor's at NASA. And she says about this, that measurement has this sort of magical property where we could say that we force an error to happen by measuring, but by forcing it to happen, that maps the continuous to the discrete errors. So that's the key thing.
I didn't understand. Before your error had an arbitrary form. Why now is only one of the polymetrics?
Because of the measurement. Because with the measurement, with the MI, I didn't specify what MI was, the measurement basis. But let's say we picked it nicely so that we'll get one of the sigmas out. And this is possible to do. And so when we did that, when I make a measurement, that this arrow here is making a measurement. This goes from the general form to one of the poly errors now.
With some probability or
with some probability. Yeah. With probability pi, you get this state.
Does I want to keep the psi the same as this?
Psi is the same. Yeah.
So psi has to be an eigenvector.
Of mi?
Yes.
No, it won't be.
But if you're destroying the state, how is that error corrected?
We'll see. We'll see. Great question. Yeah.
So does this mean that we're choosing
is a single component.
Yes, for just for sake of convenience here.
So how do we, if we don't know what the error operator, if we don't know what the coefficients are, how is it generally possible?
These are great questions. For here, I'm doing it because I know what the errors are, and I'm being vague about it because I want to just distill the principle. The principle is that we're going to get one term, and we'll see this concretely with an example with the repetition code. So yeah, you're all thinking ahead.
Also, if an I is proportional to each coefficient, like
Yeah.
if the 3 will be proportional to each,
Yes.
maybe square.
Exactly.
Makes sense.
Okay, but the questions are great. You're all ahead. So let's move on.
Could you quickly give the name of that book you mentioned?
Yes, it's called A Gentle Introduction to Quantum Computing. How gentle it is, you can decide. Okay, so now where do we start? Per usual, let's go to the classical space. So there's an idea of error correction in the classical space. If I say something and you don't hear me, I might repeat myself. If you say something, if I say something and you don't hear me, I might repeat myself. Okay, I don't need to do it again. You got the joke. But you know, with the repetition code, that's the idea. So we're going to transmit bits over some noisy channel, and instead of just doing 1, let's do 3. And let's do 3, and let's hope at least 2 of them survive. And if 2 of them survive, then we can take a majority vote. And whatever the majority vote is, that will be our correction. So very simple idea. This is known as the classical repetition code. And I just said this. So this is going to be an exercise, if I remember my slides. I want you to think about the following. Suppose each bit flips independently. So each of the physical bits, the 0, you know, one of the 3 zeros and one of the 3 ones that we're sending, flips with probability p. For what probability p, is it beneficial to use the repetition code? So p is a number between 0 and 1, it's a probability. And we want to know when, or if at all, it's better to use this for what values of p. So take a minute to think about this and discuss with your neighbor.
So this repetition code is going at 2 pretty low, not necessarily above 45, it's beyond 0.5. But even like here, if I read this, with the comment, but like I would say,
yeah, hearing some good discussion. Let's hear some ideas. Yeah, in the back.
So if the probability of 1 is p, then the mass flipping is 1 minus p. And however number you're using, that is, let's say the length is n, then you can have, let's say, 1 minus p, capital N minus something, that's the number of that didn't flip, times p to the n, and depending on p is, that will tell you the.
Okay. Yeah, good idea. Other ideas, other thoughts? Yep.
Yeah, so I feel like this repetition code would be pretty good and efficient for pretty large, or not, you know, with like, you know, maybe like 1% up to like 50%. But when you get to really low P, then it becomes a scheme that has a lot of unused redundancy.
Yeah, okay. Yeah, if P is very small, then maybe not a lot of the bits are flipping. So there might be too much there, it might be overkill. Okay, yeah, great ideas. What, maybe one more, any final? Anyone come up with a number? The answer is going to be a number between 0 and 1. Yeah. Less than 1.
Closer to 0.
Closer to 0. Okay. How much? 20%?
66 will be negative.
2/3. Okay, it'll be 1/2. The answer will be 1/2. And so here's the sort of analysis. The thing you need to do is count how many ways there are for at least 2 bits to flip. Right? If at least 2 bits flip, then in the majority votes, we get the answer wrong. We'll map it to the other bit. So to count that, it's a simple counting problem which you can't do before noon. But the answer is that it'll be like 3p squared times 1 minus p. That's how many ways there are for 2 bits to flip. And then for all the bits to flip, it's p cubed, right? And so you can simplify this. And then what you do is you set the probability of an error piece of b to be less than p. And then by solving this polynomial, you'll get p less than 1/2. Okay, so that's when the repetition code, at least for 3 bits, the 3-bit repetition code is beneficial. And this is a sort of somewhat similar to the thinking you do in error correction. So this is a good exercise to do. Any questions about this? Okay, good. So in the classical space, we said let's copy all the bits. Let's just add redundancy. So we might want to do that in the quantum space and take some state psi and make 3 copies of it. And you can't do this in general, as expressed by the so-called no cloning theorem. By a show of hands, how many people have heard of no cloning? Majority of people. So, I mean, what it says is you can't do this in general. And people say, this always gets brought up in error correction as a sort of fundamental thing. And I guess at a fundamental level, it is important. You can't copy arbitrary information, but it's not that big of a deal. And so if people want to see the proof of this, of why you can't do this, please ask me maybe at the end and we'll go through the proof. But for now, we're just going to say we can't do it in general. But I'm not going to go through the proof because there's something that we can do, which is exactly copying information. So just to mention this because it's always mentioned. And then to put even a little bit more of a tag, just an aside, this isn't really a quantum thing. So as long as you have tensor products and linearity, which are quantum, but you don't really need all of the axioms of quantum, then you'll still have a no cloning theorem. And then this is described in the very nicely in the lecture notes of Elizabeth Crossan, who's at UNM. I include the link here for this discussion. I would encourage you to look at this more on your own time. But that's all I'll say about it now. You'll hear a lot about no cloning with error correction. And so I wanted to go the other way and say that it's not that important and not even that quantum really. But now let's get into what we can do. And so, okay, so from no cloning, we can't make just copies of any states like we did with the classical repetition code. So the question is, well, can we copy anything? So I claim to you that if I have an arbitrary state psi, maybe I can't make 3 copies of that, but I can sort of copy basis information. And what I mean by that is exactly this map here. So the map is 0 will become 0, 0, 0. It looks similar to the classical repetition code. And 1 will become 1, 1, 1. Okay. So we can clone the basis information. We can repeat that. We just can't repeat the state. So I'm going to ask you again to think about how to do this. So so think about how to do this, and just a note that this can be viewed as an exception to no cloning, because no cloning states you can't do it in general, but you can do it for orthogonal states. 0 or 1 are basis states, so they're orthogonal. So you can make arbitrary copies of 0 and 1. But now think about how to do this. And this is probably the most important exercise. Or maybe I'm just trying to motivate you to think about it. But think about how to do this in a circuit. And if anyone has any ideas, please shout out.
Will these be equivalent to just repeating the circuit, the entire circuit 3 times?
It won't be. That would give you 3 copies of like the state size. So that would give you like alpha 0 plus beta 1, parentheses, alpha 0 plus beta 1, and then another alpha 0 plus beta 1.
Would a C naught gate be able to do that?
C naught's going to be, yeah, C naught's going to be important here.
C naughts on the Hadamard.
How many C naughts?
3.
3 C naughts on a Hadamard? Very close.
2.
Very close. Not exactly right, but very close. I'll give you a hint. So assume you have the state side. So, this is our input, the state side. And then the hint is that, well, not much of it. You'll have two other qubits starting in the 0 state. But maybe it's important to clarify that.
Yeah, could you just do like a C naught gate on that first qubit to the second, and then just do it another C naught from the first qubit to the third?
What do people think? Will that work? Yes. Yeah, that's exactly it. That's exactly it. So the answer is I can do a C naught and sort of write that into the second qubit and then another one here. So why does this work? Well, the C naught will do nothing to the alpha zeros, starting with the 0 control, that won't do anything. But with the 1 state, it will flip this. So with the 1 0 term will become a 1 1 after this gate. And then the 1 1 0 will become a 1 1 1 after this gate. So there's a mapping from this mapping that you see. Questions about this? Yeah.
So this can have redundancy sort of after you've gone through this part of the circuit, but what happens if there's an error before you've got redundancy?
Great question. In the full theory, which is fault tolerance, you have to say exactly this. Well, what happens if there's an error in this C naught gate? What if I can't do this perfectly? And what if there's an error in this one? What if there's an error while the qubit is just idly sitting around? That the answer is you can deal with that. It's a great question. It's the question, and the answer is the fault tolerant theorem, or the idea is in fault tolerance. But with error correction, this is what I want to make the distinction of. With error correction, we're just going to assume for now that these are perfect, to make our lives a little easier and get some grasp on what's going on. So for now, we're assuming they're perfect. That if the encoding is perfect, that's sort of the realm of error correction. When you assume that everything can be faulty, everything can have an error, that's fault tolerance. So that's the answer for now. The idea is, well, you might like repeat the encoding multiple times to fix that. But yeah. Other questions about this? No. This is one way, and I'll have a slide in somewhat, which will say some other ways. Yeah, great question. The idea is, I'll say it now. Let's see if I can find the slide. Maybe not. It's a little bit later. But the idea is we have 3 qubits, and we're going to pick 2 basis states as the sort of good ones, and everything else. So these are the code words, and everything else will be in error states. I use green because green is good and red is bad, but So for example, what are the other ones? 0, 0, 1, 0, 1, 0, etc. 6 more. These are the say the error states. So if you think about it this way, then what we're doing is we're taking an 8-dimensional Hilbert space, 3 qubits, 8 dimension, 8 basis states, and we're taking a 2-dimensional subspace, and we're calling that the good space, the code words, the logical qubit. And the other ones are, and so one way to think about this, if you pick other ones, then that can be a different way of redundancy. But great question. Okay, in the interest of time, let's move on. So, this is just the same thing, but we now get the bonus of understanding one of the things that John Preskill says. So at the bottom, John Preskill says, he has this quote: "We learned that it is possible to fight entanglement with entanglement." What does that mean? Well, as I said at the start, noise in devices is due to unwanted interactions with the environment. So that we can say the computer is becoming entangled with the environment. So that's the first entanglement here. And then if you think about this encoding circuit, what we're doing is we're entangling the input qubit with these other 2 ancillas. And so that's the second entanglement. And so we know what he means now. We're fighting entanglement with entanglement.
Right. I just want to comment. I think this could be analogous to thinking if you have something that you don't want the temperature to change too much, you couple it with something that has a huge specific heat. So now this is the fluctuations of this by interacting with the outside is not as big because it has more temperature inertia.
Yeah, this is a very mathematical treatment of error correction, which is a usual one, but there's physical analogies, and this is definitely which are very fruitful to think about, by the way. So thanks for that comment. Okay, so now we should be okay on time. Now we've encoded the states alpha 0, 0 plus beta 1, 1. And with the classical repetition code, we just know the bits that we get, right? We get 0, 0, 1 or 1, 0, 1, and then we just take a majority vote. But with the quantum case, we can't look at the states. So we have to do something else. And we need to peek at the state, so to speak, to check which errors, if any, occurred. So that's the next task. We've encoded, maybe something has went wrong. Now we need to diagnose that and fix it. So how do we do that? Well, the answer is this idea of measuring, like I said, and they're going to be projective measurements. So I'll give you an example of the first thing that we could do, and then I'll ask you questions about the other ones. But there's 4 possible things that we can correct here. The first one is a little bit cheeky. It's no error, but if we consider this an error, we can say that we can correct it. So if no qubit was flipped, then consider this projector, which is the projector onto the code space. So it's the code words are 0, 0, 0 and 1, 1, 1. And so I can sum them together and form this projector. And if I do this, and then I measure this with probability 1, then I would have known exactly that no qubit flipped, right? If any qubit did flip, say the first one flipped, then this would be a 1, so this term would go to 0, and then this would be a 0, so this term would go to 0. And so we would only measure this projector if no error happened, so no qubit flipped. Okay. So now the next question is, how can we look at this projector and modify it? And how could we diagnose? What's a projector that we could use to diagnose the error that the first qubit flipped? And first, just so we're all on the same page, will be the leftmost one in the cut. So these guys here.
You use the 1, 0, 0 and the 0, 1, 1.
Great. Do people agree? Yeah, that's the answer. So it's, yeah, I mean, it's as simple as flipping the first one. So this will still be a projector. And what we've done is we've taken 0, 0, 0, and we flipped the first one now to be a 1. And we've done the same thing in the second term. So 1, 1, 1 is now 0, 1, 1. So now we'll only ever measure this if the first qubit flips. In other words, you know, and when you do this experimentally, you don't know the error that happened. So we would try, you know, this in the first one. And if we measured this one, then we know that the first qubit flipped. So that's how you figure it out. What about if the second qubit was flipped? Question or answer, either one.
So you're doing these measurements, and I guess the state is collapsing.
Great question. It's not bad, it's good. It's good because we're getting rid of the errors. So the key thing is we now have a 2-dimensional subspace of an 8-dimensional Hilbert space. So if you want to think about a crude picture, can people see here if I draw like this? Yeah. So this is not 8-dimensional, but so let's say that these are our code words, so to speak. And if we're exactly, you know, on one of these, then we're in a code word, we're in a logical state. But what we're saying here is that some errors can happen. Some errors can happen, and we might have a state that looks like this. So when we do the projection, when we do the measurement, it's going to go to one of these. And so the question is this bad? Or, you know, usually when we measure, we destroy information. But we've done the redundant encoding first. So because of that, it will collapse to one of these. And that's good because it will bring us back to one of the code words.
The information about which relative code word.
It won't be. The information is the information is in the alphas, the A's and the B's, alpha and beta. So remember, our state is the qubit that we want is alpha 0 plus beta 1.
Right, but you know that, so then you won't be able to continue to operate on the state. 0, 0, 0.
Yeah, for example, suppose if you apply B0 and there was an error,
Mm-hmm.
so you register 0, because when you apply that operator, the projection of your state into B0 is 0. So you destroy your
No. You don't destroy the alphas and betas. What you'll have is if you
know them, but I'm saying you'll still end up, even after you do it, so you're gonna do the correction, remember, you get 0, 0, 0.
Well, I think the idea that you just do this at the end is
good discussion. Let me sort of orient this. So let's say that, okay, let's say that we had our logical state. And then some error happened and we measured this projector. Now, if we measured this projector, then we would have collapsed the superposition. And so now so this is after error and measurement. We would have alpha, we're saying the first bit flipped. So we have 1, 0, 0 plus beta 0, 1, 1. Do you agree? Yeah. So this is where the error occurred.
Isn't it also possible that there were errors on the second and third?
It could be, but yeah, there could be, but for now we're saying this is the first qubit flipped. And so if that's the case, then, so what I'm claiming is we still have the alphas and betas, so you see them here. But now we've some errors occurred, we've done the projective measurement. And then after we do that, the state it's related to the original state. So what I can do is now I can apply a correction operator. So this is the final step in error correction. If I do a correction here, it would be a bit flip on the first qubit, 0th qubit, first qubit. So if I do that, then I get back to the original logical state.
could apply something, for example, since 100 to 000. That type of trajectory where you project into 100, which is the state with the error that you have,
Mhm.
and since it, the bra is 000, which is the one that you want.
Mhm.
But that assumes that you know the error happened in the first one. I think his question, or at least my question, is how do you know that happened without destroying the information that you have to then do something?
It's a great question. It's hard to decouple them. I mean, the answer is you know by doing these projective measurements. And so why I say it's hard to decouple them, because depending on your favorite interpretation of quantum mechanics, we can say that doing these measurements causes the projection to happen. In other words, it causes the error to occur. It's a little, but yeah. So when we do the measurements, we'll get one of the error states. For example, this one. Stick to this example, just sort of be concrete. So if we do that, then we get the piece of information we get is what projective measurement evaluate to one. So let me say it a different way. I'll skip through it and I'll say we would go through and we would measure all of these. We would measure P0 through P3. And I'll explain how to do this in a few slides. And then the information we're going to get from this is 4 pieces of information. We're either going to say, this one measured 0 or 1. This one measured 0 or 1. Well, in other words, we'll see that one of these measured to 1 and the others were 0. And so if one of them measured to 1, for example, this guy here, then that tells us what error happened. And if we know what error happened, we can then correct it. That's the idea. Yeah. Hopefully that makes sense. Maybe one more question here. Yeah, good. Yeah, go ahead.
My question is that if you are doing the measurement, so in the ideal case, you shall get P naught. If you measure P naught, should that be a 1?
What do you mean should be?
I mean, if you measure or if you project the circuit, the state that is encoded in the circuit, with a projected P naught, right? So if you expect 1, right?
If you don't have any errors,
That's right.
that's right.
Then the question is that if you, the second, third, and fourth line stands for one bit left. Right?
That's right.
So what is the possibility? What is let's say, what is the magnitude of?
Great question. Well, I mean, it depends on the error or the error model that you're considering. Like you could say that one of the bit flips with probability P, like we did in the classical case, and then so that like each of these would be probability P.
Yeah.
And
so what if, for example, if we consider the flip of the qubits to be 50%,
yeah.
then what is the magnitude or approximately the magnitude of P1, P2, P3?
Well, I don't know off the top of my head, but you could work it out. I mean, it's the same counting argument as in the classical case. You count, okay, what's the probability of 1 bit flipping? There's 3 ways that can happen. What's the probability of 2 bits flipping? There's so many ways for that to happen, and then 3 bits flipping. Yeah, that's how you would
The
figure
idea
it
is that ideally you shall get the majority of the result, majority of the probability, which comes from P naught. And there's a tiny, let's say, probability for P1, P2, P3. So, for example, you have a pancake, then, for example, 80% is a P naught, and maybe the rest of the 6% or 6.6% roughly P1, P3.
Yeah, I mean that's something that could happen. I mean, you also need to count like 2 bits flipping and then all bits flipping. Yeah. But yeah.
Well, I got you.
Okay. Good. Okay, let's, yeah, hopefully we're digesting this. There's, we got about 5 minutes left, I think, right?
So you can decide whether you want, so Ryan is running 2 lectures, and then you can just take the break when you want. Then we could just do 15 minutes. So if you think it's okay to stop now, we could just stretch legs.
Let's take a short break now and people can think about this, and then we'll finish error correction and start error mitigation. Okay. Okay, thanks, Martin. Okay, so welcome back. This is where we left off. And a lot of good discussion and questions, so thank you for that. Please keep it up. And I'll try to get through the rest of what I have on error correction. That'll maybe take around 20 minutes. And then we'll transition into error mitigation. And that is that'll go a lot faster. And then we can start the hands-on stuff. So this is where we left off. Just to reiterate, we're sort of going to get this table of information, and this will tell us one of these sort of lit up, one of these was measured, and the other 3 weren't. And from that, we'll be able to know what error occurred. For example, if the first bit flipped, then we would measure P1, and we know what error happened there, so we can then apply that and get back to the logical state. So that's the idea, and we'll sort of keep touching on this, and I think it'll become clear. So okay, so this is exactly what I was saying. So I'll keep this up. It's the same table, but we're now flipping it. So in practice, we do, and I'll introduce some terminology. We do these measurements, and we call these syndromes. Syndrome is, it means sort of, what's wrong, what went wrong. So that's a term you'll see in error correction, and each of these has a meaning, and then from the syndrome we can deduce what correction operator we need to apply. And so here it's a simple case: nothing went wrong, you do nothing, and if one of the bits flipped, you flip back to the right bit. Question?
What if you project 0? There was no bit flip, but you checked to see if there was one.
Do you mean the first row of this table?
No, I'm saying you do one of these projectors and the state wasn't in that subspace. So
this is actually, this projector is not an actual gate by itself, it's not a unitary transformation. So it's going to be done in a different way that Ryan will explain later. So you either get an eigenvalue of 0 or 1. If you get a 0, it doesn't mean that the state now became 0. So you can subtract 1/2 from that projection operator, and then it's 1/2 minus 1/2, and there's no, one's not giving you 0.
Yeah, thanks, Dean. This will be sort of the thinking, the answer, and we'll see this in the next slides. Okay.
I think you see issues that every time that we have been building circuits, when you say you measure something, you have that symbol of the thing that measures, and after that, it's like, okay, you lost everything because you measured. And that's what I think everybody has, the representation have in their head, and it's like you measure that, then you apply one of these symbols.
Yeah, so the difference is that we've taken the first step, which is doing the encoding. In other words, adding the redundancy. So remember, we have now an 8-dimensional Hilbert space of 3 qubits, and we're going to measure something. So there is going to be some collapse, but it's not going to completely destroy the information. It's going to project you onto one of the basis states. And then from that, you know then how to get back into the code space.
Okay.
That's the key difference.
Okay.
If you just have a single physical qubit and you measure, then yeah, you destroy the state. But this is the difference here. Okay. All right. So that's the story of the repetition code. And here's another exercise for you. We were always talking about bit flips here. And bit flips is the thing that can go wrong in a classical computer. But as I said at the start of the previous lecture, you can also have other errors For example, we could have phase flip errors. So this means poly Z's. So poly X is bit flip, poly Z is phase flip. So think about for a minute, can we modify all this procedure that we just went through to now correct for phase flip errors, poly Z, instead of bit flip errors, poly X? Hearing some good discussion. Any ideas? Can we modify this for phase flips? Yeah.
So if you apply a header mode before it goes into the channel, then if there was a Z in the middle, it's just in H and so it's like that. So
Yeah, exactly right. That's great. That's great. So the idea is we can do exactly the same thing with one minor change, which is just, as was said, recognizing that X and Z are related. And they're related by this change of basis. So what does this mean? So this is just an identity that I think we've seen before. If not, you can prove it. And so instead of mapping 0 into 3 copies of 0, we can map it into 3 copies of 0 plus 1. So that's what's shown here. And remember, so you see the relation here. Hadamard acting on 0 is this state, 0 plus 1. So what we do is instead of coding 3 copies of 0, we do 3 copies of this state. It's called the plus state. And then we take 1 and we do 3 copies of the minus state. And this is exactly the change of basis. And you can update the syndrome measurements in exactly the same way. I have it as a question, but the answer is that it's the same table from the previous slide, but everywhere you see 0, you replace it with a plus. Plus meaning the plus state 0 plus 1. And everywhere it's a minus, everywhere it's a 1, you replace that with a minus. Minus being the state 0 minus 1. So that's the answer. So we can use exactly all the same framework that we just developed for phase flips. Yeah, go ahead.
In this case, do you need to worry about error for the half life?
Yes. But we're assuming for now that there won't be an error there. Yeah, it's a great question. As I mentioned in the first lecture, in practice, you have to account for errors occurring anywhere. And that's the sort of realm of fault tolerance. Here with error correction, we're just going to assume that some things are perfect. And that's the idea here.
It's like when you have a circuit and you say that nothing has resistance except the resistor. But if you have an inductor in the circuit, the inductor has a resistance, but it's very tiny, so you're ignoring it for paper first.
Yes, yeah, exactly. So moving on, here's a hard question. But I want you to think about it. If anyone comes up with an answer to this, you would have been on the same wavelength as Peter Shor in the 90s. So can we correct for both bit flip and phase flip errors is the question. So now we have 2 codes. We have the bit flip repetition code and we have the phase flip repetition code. They're similar, but one corrects for bit flips, the other one corrects for phase flips. But that's not the most general error, as we know. We can have both a bit and a phase flip. And either one of these codes individually would not be able to account for that. But is there anything that we can do to be able to account for that?
Arm these errors together, you already showed just the Y matrix and Y represents the next
Okay, good idea. However, if we have, say, a poly y here, then so in this example, there's a bit flip on the first qubit. If I now add a phase flip to get something like a poly y, then that maybe that would change like the sign here. And so if I was just using the bit flip code and I did the correction, I would get the 0, 0, 0 and 1, 1, 1 right, but then I would have the wrong sign here if I did the same correction. So you have to account for that as well. But very good idea. And then the other thing is you can think about maybe on one of the qubits a bit flip error occurs, and then on the other one a phase flip error occurs. So not just the products, but they can happen.
Well,
So-
I was gonna say my intuition would be to just run the bit flip correction and then the phase flip correction in sequence. So on your first pass, you kind of wash it for bit flip errors, and then on the second pass, you wash it for phase flip errors.
This is a very good idea, and the answer will be something similar to this, if I understand you correctly. Not exactly this, not quite sequentially, but sort of sequentially.
Gotcha. I think the first you have flips, and the second type is you have phase. Using that on the first one, just X, the X matrix was applied, and the second one, the C matrix was applied. This is just the Y matrix was applied.
Yes.
So if you, I'm trying to, but I haven't finished, to write everything we did, just not thinking of flipping, but thinking I apply X, I do this, I apply C, I correct this way. This will be I apply Y, I correct in whatever way you need.
Okay. Okay. Good thinking. Good thinking. It's, something like that will appear in the answer. There's maybe one more idea in the back.
Is it possible to like repeat with more bits and then certain number of bits correct bit flippers?
Very good. Very good. This, I think I'll say, this is the answer, I think. The idea is the following. So in error correction, there's the idea of concatenation. So this is similar to sequential, but not exactly. You'll do sort of two steps of the encoding. So step one is that you'll apply the bit flip code. And then step two is that you'll apply the phase flip code, sort of you'll concatenate it. So you'll have more qubits, as you said. If we use 3 qubits for each, then we'll have here a total of 9 qubits. So let's see an example of what this means. Color coded. So we start with a physical qubit. This is what we want to encode. This is noisy. We need to make it not noisy. So let's apply the bit flip code. We apply the bit flip code, then we get 3 physical qubits, blue, green, and red, and they're all in the 0 state. So now the idea of concatenation is we take each one of these physical qubits in the encoded state, and we now map that using the phase flip code. So remember, the phase flip code takes 0 and it takes it to the plus state. So you take this physical 0 and you make 3 qubits and you put it in the plus state. You do the same one for the green one, and then you do the same one for the red one. And that entire state of 9 qubits is now what you call logical 0. Seeing some squints. Quick questions about this? It won't be exponential. I'll say at the end some sort of the sort of current state of affairs. It'll be a lot. You'll need a lot of physical qubits, like say 1,000, but it's doable, hopefully.
So you're saying this won't scale as a power, like, or 2 qubits it would be 18, it would be less.
Oh, I see. You won't always need to do this idea of concatenation.
Oh,
This is something that you can do. you can take two individual codes and sort of make them stronger. And I see why you mean exponential now. Yeah, 3 squared is 9.
Yeah.
But you don't always need to do this. Yeah, very good question. Other questions? Yeah.
I think the overall logic in the mission is that you're going to fight entanglement, or fight the noise with entanglement, right?
Yep.
How can we interpret this sentence up here? I mean, how can we interpret the role of entanglement here?
When I bring up the circuit, that'll answer the question. I mean, the way you encode this, like before, is with C0 gates, and the C0 gates will entangle the state of the qubits. So in other words, there's entanglement in this state, in the encoded state.
We are saying that if there is entanglement between a copy and copy state, right?
Yes. Yeah, good question. A little low on time, so I won't ask you what the one state will be, the logical one state. I'll just tell you the answer. But it'll be a similar thing. We'll do the repetition code. So 1 will become 3 copies of 1. And then we'll do the faceflip code. So each of the 3 copies of 1 will become the minus state. So it's similar to the 0, but with minus signs. And how do you do this in a circuit? Okay, so the logical state is this. More notation that you'll see if you're so inclined to look into error correction after this, then the bars over the states mean logical. So that's what's meant here. And the circuit for doing this might look like the following. So the first portion for doing this is exactly the same thing that we've seen before for the bit flip encoding. So this was the 2 C0s. We saw this. It's spread out because we have to fit the other qubits in there. And then once we have that, the encoding for the faceflip is the Hadamard and then the C0s. So that's how you would do this encoding in a circuit. So I wanted to mention this because it covers concatenation, which is a powerful concept in error correction. And this was the code that Peter Shor introduced in the sort of the bit of history at the start. So this was the one that he introduced from his paper. So I would encourage you to look at that, and you'll see this code in there. And this was the first one, sort of historically, which could correct for arbitrary single qubit errors. Now we can say arbitrary single qubit errors, not just bit flip and face flip, because the product is also correctable, and the product is poly Y that forms a complete basis. Okay, I've hit on this a lot because there's a lot of great questions, but just to re-emphasize, here is finally the slide on it. The distinction between error correction and fault tolerance. So just to very briefly reiterate, error correction, we're making some assumptions that things are perfect. We're just trying, getting ourselves in the ballpark, making our lives a little easier. Fault tolerance is the real deal. Now, this is, you're at a company, you want to build a quantum computer, or a university, whatever. You can't just assume that some things will be perfect. You have to account for errors everywhere. So that's ballpark with this differences. The second note is what I've drawn on the whiteboard here, almost in the same colors, but opposite. So this is the idea of redundancy versus partitioning. So I touched on this a little bit, but I'll say it again. You can think about this in both ways. With redundancy, we take 1 bit and we map it to 3. And so you can think about it that way. Another good way to think about it, though, is this partitioning of the Hilbert space. So with 3 qubits, we have 8 basis states. And to have a qubit, a logical qubit, that's a 2-dimensional thing. So we take 2 of these basis states, 0, 0, 0, 1, 1, 1, and we call those the good ones. Those are the code words. And every other state that appears there is now an errored state. So you can think of this as a 2-dimensional subspace of a larger dimensional Hilbert space. That's what a qubit, a logical qubit is. Okay, so both are good ways of thinking about error correction. The last thing, and then we'll be done with error correction, is introducing the idea of stabilizers. So if you look in the literature and even textbooks, everything, you might see projections at the start, and that's sort of the way I did it here. But in practice, when you analyze these things, you always use what is called the stabilizer formalism. And it's related to the projections in sort of the following way. The purpose is that we're going to not measure these projections anymore, but we're going to measure stabilizers. And that's going to tell us the same information as what sort of these projectors are intuitively telling us. Projections on each one of the correctable errors, the states that we can correct. So let's see how this works. Yeah, as I say here, there's a more succinct way to sort of express the stable and determine which errors occur. And that's the idea of the stabilizer formalism. So let's consider this example. Let's say that we measure the operator. Still think about the sort of three qubit repetition code. Let's say that we measure the operator Z on the first qubit and Z on the second qubit. So you can write this two different ways here. Well, what does this do? So a way of writing poly Z, which is very helpful here, is it's the projection onto the 0 state minus the projection onto the 1 state. I think we've seen this before in the first hands-on session when we did expectation values. So if that's the case, and I take the tensor product of two of them, there's this is just substituting in Z tensor Z. I'm not including the tensor product symbol, but ZZ is understood to mean the tensor product. So that's what this means here. So if I do this, and then this is just the definition, and I rewrite it a little bit, I can see it in the following way. So just by expanding these four terms, I can write two of them with plus signs, and that'll be the +1 eigenspace of this operator Z tensor Z. And what you see in this space is that in the cuts, the two bits are the same. The two bits are the same. The other two terms come with a minus sign, and in the -1 eigenspace, the bits are different. So what does that mean? I'm thinking of the two bits in the cuts, and here, for example, they're different. Here they're different. Here they're the same, and here they're the same. Okay. So if I measure poly Z, this product Z tensor Z, then I'll get a +1 or a -1, two outcomes. And from that, I'll know whether the bits were the same or the bits were different. So that's what I'm saying here. Z1, Z2 will ask if the first two bits are the same or different. And similarly, Z2, Z3, just shifting the index, will ask if the second two bits are the same or different. And I'm still thinking about the repetition code, 3 total qubits, do Z on the first two and then Z on the second two. And so my question to you is, if you're given this information, what information? Well, whether Z1, Z2 was +1 or -1, and then whether Z2, Z3 was +1 or -1. So two bits of information. Can you determine which of the 3 bits flipped? So in particular, let's be very concrete and give an example. Let's say bits 1 and 2 are the same. So we measured Z1, Z2, and we got a +1. And bits 2 and 3 were different. So Z2 and Z3 was measured to be -1. Can you know from this? Can you determine what of the 3 bits flipped?
Is this under the assumption that only one?
Yes, thank you.
Okay, then yeah.
Okay. Do people agree? How many say yes? How many say no? Okay, it is yes. So what bit flipped here?
Yeah, it's 3.
3? It is 3. Does everyone see that? Any questions about why the third bit flipped here? Yeah, that's one way to think about it. Okay, I think we're all good with this. Yeah, you just sort of reason it through. I mean, you can draw out, 001 is an example which would have this syndrome information.
Yeah, if only one tweet, then two things are the same, they are the correct ones.
Yes, exactly right. Okay,
Like signaling you 3 is the. Oh,
very good. I think we're all on the same page. How about bits 1 and 2 are different, but 2 and 3 are the same?
one is-
So which one flipped?
One.
1, very good. What if they're both different? 2, very good. Oh, and the next one came for free with the slide here. So if they're all the same, then no bits flipped. Okay, very good. So this is the idea of stabilizers. So let's formalize this a little bit. So first note that this is exactly our table from before. It's not in a table, but remember we had this table where we were saying, okay, well, no bit flipped, the first bit flipped, the second bit flipped, or the third bit flipped. And now we have a different way of expressing the same information. And there's a one-to-one mapping. So now the idea is, let's forget about these projections. Let's measure these stabilizers, Z1, Z2, and Z2, Z3, that'll tell us the same information. Then from that information, we know what error occurred, and then we can then correct for it. Okay, so same table from before. A question to consider is whether you can do this with Z1, Z2, and then Z1, Z3. What do people think? Yeah, it'll be, you'll have enough information there as long as you can compare, two different ones. Then that'll work as well. And we'll see mathematically why why that's the case. So, oh, I did put it on the table. That's nice. It's almost like okay. So here's the table now with syndrome measurements. So with the syndromes, again, we're measuring Z1, Z2, Z2, Z3. Each one will give us 1 bit. There's 4 possible cases. And the things you see here in parentheses, just again, hammer on the notation, are called syndromes. So these are, in this case, 2-element vectors, but binary vectors that we call syndromes. Each one of them corresponds to a specific correctable error. And from that, we can determine what the correction operator is. So that's the idea here. Yes.
I'm a bit confused. Are you saying that based on the measurements, you are going to insert the public circuit specific gate?
That's right, the correction operator. That's right.
So then, if we visualize this to be in the middle of a certain circuit, so based on the measurements or partial measurements in the middle, we're going to insert or make some of the gates size there.
Yep, you'll have to have this conditional feedback where you do measurements, you look at the measurement result, you very quickly figure out what went wrong, and then conditional on that, you apply a correction operator into the circuit. Now, you don't always have to do it actively. You can sort of keep track of what went wrong, and then sort of keep the correction, and then sort of percolate that to the end. But you can think about it as not for now. Yeah, you would apply conditional correction into the circuit.
Is this realized? I mean, is this already in the industry?
Yes and no. I'll say the last slide will be some papers that have done things like this, but no one has really demonstrated. There's been a few like experimental error correction demonstrations, and with hardware like IBM, I think they're starting to support the notion of like classical feedback. Really for this reason and others, you can do other things with it. So not quite there, but close.
This is really conceptualized. You're going to use a classical bit to control the
Yeah, you'll have to use the information you get out of this to determine what the correction is. Yeah. Question?
Is the benefit of using stabilizers just that it requires pure measurements, or is there more?
Definitely that, and then it's just easier like mathematically to analyze, and we'll see that. All papers on error correction, at least stabilizer codes, use this formalism. It's yeah, and we'll see not why right now. So I'm calling these stabilizer elements, and what does elements mean? Elements of what? Well, let's look at these two stabilizer elements that I called out, Z1, Z2, and Z2, Z3. And if you write down the +1 eigenstates for each, then there will be 4 of them, sort of splitting the Hilbert space in half. And you can reason why this is. Z1, Z2, the first 2 bits have to be the same. Z2, Z3, the second 2 bits have to be the same. And I've bolded this sort of the set intersection. And you'll notice that these code words in the intersection of these 2 sets are exactly the code words of the 3-qubit bit flip code. So we see that here. And the idea is that they're elements of the stabilizer group. So the stabilizer group is formed by considering these 2, for example, these 2, Z1, Z2, Z2, Z3, as generators. These are going to be generators for the group. And so what does that mean? Well, in the group here at the bottom, you see each of the generators. But then I can take, with generators, you take products. So if I take the product of both of these, then I'll get Z1, Z3. And then I can also square each individual one, I'll get the identity. So this is a group, and this is known as the stabilizer group. The +1 eigenspace of this stabilizer group is now exactly these code words. So you see the relation. Yeah. Question.
So this group is defined by like a binary operation, right? And you can, with just 2 of these elements, you can map to to all 3 bits. But does this generalize to systems with, say, like 5 bits?
It does. It does in a sort of very natural way. I mean, so for 5 bits, I don't have an example, but we can just think about one. Then you would write down sort of what the stabilizer generators are. And now instead of being, polystrings on 3 qubits, it would be polystrings on 5 qubits, or up to 5 qubits. But then besides from that, the formalism is still the same. You still have stabilizer generators, which define this group. And then the procedure is exactly the same. You measure each one of the generators. And then from that, you get the syndrome information. And then you can do the correction.
Gotcha. I guess I just had a misconception that it was meaningful with this conception that like a binary operation of 2 elements would theoretically span the entirety of the 3 bits, but I guess that's not necessarily as meaningful. Like that.
Yeah.
Yeah.
I think I see what you mean. Yeah. In terms of just the sort of framework, it's the same, independent of the dimensionality or yeah.
Gotcha.
Yeah. Okay. I promised you 20 minutes on error correction. I think we're now more at like 40s. So let's try to. We're just at the end though. We're just at the end. So okay, I said this. This is the group generated by them, and the idea is this is a subgroup of P3, which is to say the poly group on 3 qubits. So we've now reached the point that I sort of want you to think about error correction, which is the following. You consider the n qubit poly group, so it's a Pn now. You consider a subgroup of that, and that's the stabilizer group. There are some restrictions, but not many. And from those define the code space, and they tell you what to measure in the circuit to get the syndrome. So that's a very nice and succinct description of error correction. This is the stabilizer formalism. And okay, I said this too, the subspace is spanned by 0, 0, 0, and 1, 1, 1. Those are the code words, very good. So just a little bit more context, history, whatever. This was introduced by Daniel Gottesman in his PhD thesis in 1996, where he was at Caltech. And if I recall right, supervised by John Russell. And Daniel Gottesman is still very active in error correction, now at Perimeter Institute. And okay, I said this in words too. So it's a very convenient abstraction. sort of very roughly thinking, pick a stabilizer group, and that defines a code. Okay, here's the current state of affairs. This will be the last two slides on error correction. So we've really hammered this repetition code, and I'll just skip the first experimental paper by the Google group on error correction is actually using this repetition code. So they're correcting bit and place flip errors, and they call it cyclic error correction, but same idea. So that's good. We have some motivation. I encourage you to read this paper. I'll come back to this for the other two. But what Google and other groups are pursuing is a different code. This is sort of the prime candidate, known as the surface code. And the surface code is nice because you get this diagram. So what's going on here? We're not going to cover all of it, but I want to tell you, you now have the information to understand this. So what you see in this picture is a grid of qubits that lives on a surface. And there's sort of two varieties. There's black and white dots. So the dots are the qubits. And the black ones are what are known as the data qubits. So you can think about these as, well, let me not say that. The white ones are the ancilla qubits. And the ancilla qubits are there so that you can measure the syndromes and read them out that way. For example, a way that you would do this is shown in the following two circuits here. And what this picture is showing is that it's defining the stabilizer group of this code. That's exactly what you see here. So the poly Z's in green, for example, for each physical qubit, you would measure poly Z between its sort of four neighbors. And similarly, you would do the same for poly X, sort of laid out in this pattern. But what it's defining here is the stabilizer group. We now know what that means. And the eigenspaces are listed out here. So ground state energy, G is 0 here, excited state, E is 1 here. But it's exactly the same thinking that we were doing, just for the simpler example of the repetition code. You also see on the bottom of the left is a circuit for actually doing the stabilizer measurements. And we didn't cover this, but you can sort of reason through this yourself, that you can read in the syndrome information by doing C-naughts and maybe with some Hadamard's. And the way you get it out is by measuring. So these are the ancilla qubits. The white ones, or maybe I put it in the picture, black one ancilla. So here you measure these, and then this will give you one bit of information. When you measure all of them, you have some number of bits, and that's the syndrome. From that, you can figure out the error and then correct it. So more involved, but the same framework that we've just built up. So you now have the information to sort of understand this.
Right. Where is the information on the circuit flow going in the picture? Like, I have been used to seeing circuits from left to right, and now I have a surface.
Very good. So time would be going perpendicular.
Exactly, yes, that's what.
Yeah.
So you have a bunch of cables, like this qubit bits going in this direction, and you're. Oh, okay, exactly. So you have repetitions on each one of the logical qubit or physical qubits that you want to have.
Exactly. Yeah. It's now a two-dimensional layout of qubits, and the circuits here are showing like one example of this. So this here, is now time left to right of this. For example, this qubit here, or this one's Z. So maybe this qubit, and this is how you would do the stabilizer measurement. Yeah. Okay. So let me just say one word about why these codes. Why the surface code as the repetition code. The surface code is very nice because it has this notion of being on a surface, a grid, which is something that you can experimentally do. It has a very high threshold. So the threshold is something that I did not introduce, but the threshold is the physical error probability that you need to be below in order to be able to have fault tolerance. So the surface code has a high threshold. So that's nice. And then the syndrome measurements to do this, there's this notion of locality. The locality, geometry local. So you know, you don't have to do like say a C naught between this qubit and this qubit or something. You can lay it out on this grid and it's all local. So these are all desirable features as well as a few others. How large does the grid need to be? Roughly like the estimate is like 1,000 physical qubits per logical qubit. And there's a lot of factors that play into that. The larger the grid is, the higher the distance of the code, which means the farther the code words are from apart from each other. So that means, just very quickly, there's less likely of a chance of having a logical error. Logical error meaning like you think 1 bit flipped, but actually 2 bits flipped, like in the repetition code. So you would correct it to the wrong thing. So larger grid means less likely of a chance of that happening. Okay, and let me just leave up these papers. So I talked about the one about the repetition code from the Google group. There's another one from these folks at a bunch of different places about doing an experiment in error correction with trapped ions. So that's the one at the top. And then recently, in the lower right, from the group of, I believe, ETH Zurich, there's this paper about the distance 3 surface code. So doing this experimentally. And you can see that these are all very recent, like last year, last month. And so you now from this have a very good head start on understanding this. Okay, so that's the last about error correction. And maybe we can take a short break here, and then I'll say there's just a few slides about error mitigation. There's much less theory here. Let's look a lot faster, and then you can get into the hands-on part. The idea of why error mitigation versus error correction. So again, to the motivation, there's noise in the devices. We need to do something about it. Error correction is the big long-term solution. But because of this 1,000 physical qubit thing and other considerations, you can't do this right now. But you all want to run some computations, maybe about nuclear physics, and there will be errors that happen. And so now the question is, can we do something without this long-term theory of error correction? And that's the idea of error mitigation. So we'll take a break now, we'll come back, I'll have a few slides, and then you'll implement an error mitigation technique yourself. So that's it for now. How long is the break, Warren?
So we have a coffee break, so we were thinking of beginning again at 11.
Perfect.
We could do that. So get half an hour.
Yep.
And then you do the hands-on and the error mitigation.
Perfect.
Yeah, cool. Thanks.
Okay, great. So this is now the hands-on session, but let me just say a few words at the start about error mitigation. So we went through this whole 2-hour dance about error correction and built up a lot of theory. And we said at the end, it's hard to experimentally do. If you do an experiment in error correction, you could probably write a paper about it. That's the current state of affairs. So, but we want to be able to do something because we want to use quantum computers, say to simulate nuclear physics. We want to do something. So what can we do that's not full-fledged error correction? That's the idea of error mitigation. Okay, so you sat through 2 hours now, so you've earned a meme. And so here's error mitigation in a meme. It's very simple. This will be a lot quicker than the error correction. So we want to prepare some state psi, some perfect state psi, and NISQ, I think maybe we've seen this before. NISQ is noisy intermediate scale quantum, sort of means current state of affairs. The best we can get is the state psi passed through a channel. Okay, and what does it mean to pass through a channel? This just means the noisy state. Yeah.
Can you move the bar a bit more than stuff?
Yeah. Thanks.
You don't want to see me talking?
I can hear you.
And do you want to record this?
Is it recording?
It's already. My goldfish memory did function. I just didn't need a reboot.
I don't think it's recording.
No, it is.
Oh, it is?
Yeah. You just even
On a
hear
different
you.
machine.
Oh.
Yeah, I think we're good. Yeah. Okay. Thanks for that. So okay.
I'm not that old.
Okay, so the state pass through channel means the noisy state. But mathematically, what does that mean? I mean, we won't really need it too much here, but you'll see it, in the future. And so let's just define it. So this map, script E, is called a channel. And what it is a completely positive trace preserving map. Okay, trace preserving is intuitive. That means it preserves the trace. Positive means it maps positive operators to positive operators. And completely positive is a little bit of a stronger condition than that, meaning that when you extend it to larger systems, it still remains positive. But just think positive. And why you want it to be positive and trace preserving is this maps quantum states to quantum states. So we saw density matrices before. So this is the sort of general map. It includes unitaries. So unitaries are completely positive trace preserving maps, but also other things. And the other things are the noisy things. For example, we talked about bit flip noise in the error correction talk. We can write this as the following channel. So if we say a bit flip error, which is poly X, occurs with probability P, then we can write this as a channel where the input is some state rho. So maybe we think about this as a noiseless state, some quantum state. And then the output is this convex combination of 1 minus the probability of a bit flip. So it's to say no error. You still have the state rho. And then with probability P, you get the state rho, but with the bit flip. That's all I'm going to say about channels. There's a lot more you can say about channels, but sort of all we need for now. And really, I just included this because I made the meme before, and I assumed that audience knew what a channel was. But okay, so here's the idea of error mitigation. Here we usually frame this as wanting to compute an expectation value. We saw this a lot in this school. For example, with VQE, we were always computing expectation values of some polystrings to get some, say, energy. So our expectation, no pun intended, is that we prepare the perfect state psi, and for the observable O, we're able to just evaluate that. This is what we would expect the perfect quantum computer to do. But again, the reality is that we don't get the perfect state psi, we get it passed through some channel, for example, maybe the bit flip channel that we saw. And then I think Alexi talked about this. You can evaluate expectation values with a trace with density matrices that looks like this. But this is just so the expectation value. Okay, so the idea of error mitigation is you can roughly think about it like this. So these are the things that we have. Just look at the right-hand side now. These are the things that we have. So maybe we can parameterize the states that we prepare, the psi j's. So we can parameterize these states. And we can also think about maybe we can parameterize the channel as well. This might seem a little weird, but I'll explain this with in the next slide. And then so we're parameterizing this with I and j. And then maybe we can add some coefficients and try to just sum these together with these weighted coefficients to get closer to the correct expectation value, what our expectation would be in a noiseless case. So that's pretty much it. This encompasses a lot of error mitigation techniques, and in particular, the one we'll look at today. Questions about this? Yeah, I told you less theory than error correction. So let's look at one of them. This is the one that you're going to do in the hands-on notebook. You're going to implement this. So error mitigation, broad thing, now zooming into one particular technique, which is called zero noise extrapolation. We'll understand why they picked that name. This was introduced by the IBM group in, I believe, 2018, and also by a group at Oxford a little bit before that independently. Question?
So when you vary the trace, that's some measurement. How do you know the trace is there to trace preserved? Maybe part of this loss.
Oh, you can have channels that don't preserve trace. Yeah. For now, let's just say they preserve trace. I mean, it really won't matter too much, but you can have, yeah, there are channels which do not preserve trace. Yeah. Any other questions? Yeah.
Can we jump to the previous slide?
Yeah.
So the idea, what are you solving for?
You want to compute, so this is sort of assignment.
Yeah.
Think about it assigning this. So we're going to do something like this to try to compute this, which is the perfect value.
And what is the coefficient CI, J?
Something that we can pick. Yeah, so we can pick the psi j's, we can pick the EIs, and we can pick the coefficients. And that's sort of the error mitigation technique.
Do we have any principle or a guide to how to pick these?
Let's see one. Let's see one. So let's see zero noise extrapolation. So this, I showed this channel, the bit flip channel, and this was parameterized by some real number P probability. And so let's for now assume that we can scale that. Let's assume that we can introduce some what I'll call scale factors, lambda1 through lambda k here, which will be real numbers larger than 1. And if we do that, we can think about laying this out on a plot. So here's the scale factors, the noise scale factor is lambda on a plot, that's the horizontal axis. And then the vertical one is the expectation value that we want to compute. Okay, so we want to get to zero noise. Zero noise is good, that's perfect. But there's this base hardware noise, which in our language of scale factors would mean scaling it to just scale factor of 1. So, so we can't get to this directly, but the idea of error mitigation, or zero noise extrapolation rather, is to realize that you can go to the right. So you can go to the right, you can artificially increase the noise in the system. So the blue points that you see here are raw data that we collect. And this was from an experiment. And once we have that, then we can see some trend line in it. And maybe you have some expectation, ideally, of what the trend line should look like. And then you can fit a curve to that. Here we knew that this should decay exponentially for this example. So if I now do an exponential fit to that data, then we can do that. And you now know what I'm going to say. We can take that fit now and we can evaluate it at a scale factor of 0. And that will be the zero noise extrapolation result. Pretty simple, yeah. Kind of a clever thing, let's scale the noise instead of directly trying to decrease it. But other than that, that's the idea. So this is what you're going to do in your hands-on part. And we can start to bring that up and let's see if there are any questions in the meantime. Question?
In this case, sure, but why is it just unextrapolated?
Great question. You can construct some pathological examples where there really won't be a trend, but in most cases it will follow some trend, and in most cases you'll have some notion of what that decay should look like. Like here it should be exponential because we were measuring like how long the zero state would stay in the zero state, and that's known to fall off exponentially. So if you have an idea of what that should look like in your computation, which in several cases you do, then you can fit that there. But you're absolutely right. In principle, could be anything. In practice, in most cases, it's something that you can fit. Like, yeah.
Not a question, a comment. Again, an analogy. I think I have seen these when people are doing things like you're trying to calculate like magnetizations or something like that for a finite temperature, and you're trying to extrapolate. The temperature is messing up with your correlations of something exists like magnetization, and you can see how that correlation decays with temperature, and then extrapolate to a lower temperature that maybe you don't have access to.
Very
and
good.
temperature is acting as a noise thing that is this thing should be really correlated. You're not measuring that much. That's because of the temperature. You can get the behavior of that, and then.
Very good. I didn't know this example. Thanks for that comment. Yeah. So. Yeah. One last question.
Again, how do you interpret that question? The previous slide.
This one here. Yeah. Okay. Very good question. So it's easiest to think about it sort of procedurally, and this is the way you'll do it in the notebook, which is get the data, fit a curve, extrapolate the zero noise.
And how do you?
Yeah. The way this relates back to the equation is suppose you have the best fit. Then when you evaluate that at zero noise, it'll be for the example we'll do, it'll be like a line, we'll just do a simple line. And you'll have a best fit coefficient. And you can write that best fit coefficient in terms of the data that you collect. So the data that you collect here is the scaled, I'm writing it here as the scaled channels. And so if we go back to this equation, here's the channel that we're parameterizing. Say the state's fixed. Then the CIs you can determine by the best fit line or whatever to that data.
So, I mean, in this case, I think the best fit for a certain channel, like the channel is pure, then it should be, let's say, on the projection of phase of so just like the reality stuff.
I'm not sure. Let's talk about this individually, and then let's just bring up the notebook now so that we can start working on this. So we have enough time to finish. I'll come talk. But so the notebook is here, and I think Morton also said it's in lecture 11 as well. Yeah. So lecture 11 at PYND, and you'll find the notebook here. It should look something like this. We all know how to run this, set this up now, hopefully, but if not, we can help. And this is going to be you implementing zero noise extrapolation in Qiskit. So you'll do it for a simple example, and you'll see how well it works, and then you'll be able to generalize it and then apply it to more sophisticated computations that you might want to do it on your own or that you've also done in this tool. So let's get started on that, and I'll be walking around answering questions.
Yeah, he also, but I was thinking, you know, how they discovered only the so it's an extrapolation, but it is an extrapolation you discover because it was a different.
No, without a doubt, yeah. You know,
So, but I was thinking here, right? So
Yes.
it's a good assumption, but what if there's some weird stuff?
yeah, and that's the name.
Yeah.
I mean, that's it, yeah. I was thinking, as I was saying, if